So we're checking to see whether this sequence converges or not. E to the n over n. Now, I gave you 3 possible tests: convergence test 1, convergence test 2, convergence test 3. The last one is the one with a special name, what do you call it? The ratio test. Number 2, we can call it the constant test. That's when you have a sequence like that, where C is a constant. And then the other one, where if the limit if the limit as n tends to infinity of a sequence is equal to 0, then, and you're testing to see if xn converges, and then you realize that xn now can work like this. Then you know that xn converges as well. Of course, that's not this. The wording said let xn be a sequence, and suppose that there is an x in R, such that the sequence minus that x is always going to be less than or equal to the sequence that you know converges, which is this one here, the n. Then xn will converge as well, and the limit is equal to this x value right here. And I showed the three examples of them. So now that we got this sequence up here, which test do you think would be applicable out of those 3? Let me circle them again. Would you use the constant? Well, let me not call them any. Would you use that one, this one, or the ratio test? What's the ratio test again? The ratio test is testing the limit here. Plus 1 over xn. Those are the 3 possible tests we can use. Which test do you think will be applicable right here? You have them in the book. I'll just summarizing them.
Sir, the constant one?
Why would you use the constant one?
Because it looks similar.
Well, you would be right if it was just this. Well, because you have the n below it, the constant one wouldn't be applicable. The constant one only works if you have a constant raised to the n. But in this case, we have an n dividing as well, so we can't use that one. All right, so here's a little advice. When in doubt, use the ratio test. If you can't see how to use any of the others, like if it's not straightforward, then use the ratio test. So make a note of that. When in doubt about which test to use ratio test. It's usually applicable to most of them. Even the one that's constant, you can check the ratio test with it. Use it, it works out. It's like integration by parts. Most integrals you can't do them when you're not able, when you're not sure which integration to use. Try by parts. Similar type of thing. Anyway, so we're going to use the ratio test for that sequence there. The e to the n over n. So let me write the ratio test again. The ratio test is, we're going to check to see what L is equal to for your specific sequence, which is going to be x to the n, where x sub n. Oh, Anthony really can't come. Oh, wait, somebody came. Who is that? Okay, yeah. Oh, well, sorry for Anthony, we have at least 3 of you, so you can watch the recording. All right, so L is equal to the limit as n tends to infinity of that sequence over the next one. And remember what happens if L is less than 1, the result, remember I know. If you test this limit here and you get let's say 0.5, that's not the limit for the sequence. You're checking to see if the limit, remember this xn plus 1 is using this sequence right here. You want to put the n plus 1 in there and then put the n in there and divide. Now you're checking to see if that limit is less than 1, then the sequence converges and the limit is equal to 0. If the L is greater than 1, then then this sequence over here, let's call this the xn. They didn't give us a name, but let's just check it. Call it xn. Then that sequence is unbounded and then diverges. So we're going to test it now. We're going to test to see what that L is equal to. So our L will be equal to the limit as n tends to infinity of e to the n plus 1 over n plus 1. And we're dividing by the same thing, meaning the same xn. All right. Michaela, oh jeez, I was going to ask if she saw this before, but oh no, German is one gone. Michaela is still here. Yes, Michaela, you saw this before? Were you at the class when we did this, or did you watch the recording? Michaela? I see your mic is coming on, but I'm not hearing her. Laffer, are you hearing her?
No, sir, I'm not hearing her.
Oh, but each time I say something to her, so your mic comes on. But Michaela, probably just type yes if you saw it before, no if you didn't see it before, because I'm not hearing what you're saying. Oh, good, good, good. All right, so can go quickly then. So we're going to do our flipping. So this is going to be the limit as n tends to infinity. So now I'm going to put them together in my way. So we don't need absolute value anymore. All of those are positive. I don't even need this anymore. So this is e to the n plus 1 over e to the n times n over n plus 1. There's the limit of all of that, which is equal to the limit as n tends to infinity. I'll keep doing this stuff for you. It's going to be, what's going to be left? The limit of what? Simplify it as much as you can. What's going to be left? Come on, people. Hello? Oh.
N times e over n plus 1.
Correct. Because the e to the n cancels. Because remember that e to the n plus 1 divided by e to the n, just subtract the n. So we get e n. Probably should I put ne because that looks like e to the n. Anyway, this is e times n. I'm sure you know that it's e times n over n plus 1. All right. So, any idea what's happening here now? What do you think that limit is? So the e is a constant. You can do this with it. You can actually take out the e because there's no constant. There's no n with it. Oh, Anthony's here. So we're all here. So we have n over n plus 1 left. So it's e times, we may learn that you can take out the constants when you're doing a limit. So what do you think that limit is equal to now?
0.
0, you say. Why 0? All right, think about this, Lafern. Let's say n is 1,000. I could start simpler than that, but anyway, let's say n is 10. How much is that going to be equal to? Anybody? Not just Lafern. Why does everybody keep joining and leaving? Jermaine is gone again. Anthony, you're here to stay? Good connection now? Are you hearing me? No, I'm gone as well. What is going on here? All right. let's say, okay, so when n is 10, what is that equal to, Lafern? All right, tell you what, use 9. That's easy to calculate. When n is 9, what is that?
0.9.
All right. Suppose n is 99. What is it?
0.99.
Suppose n is 999. What is it?
0.999.
You see where it's headed?
Yes, sir.
Or is it going towards?
1.
There you go. Because you see the one in the denominator is going to be insignificant when n is like getting larger. The bigger n gets, the more insignificant that one gets. Like you're going to get like 9,999,999,999 over, what did I say? I don't remember what I said. Over like something plus 1. So it's going to, when you divide it out, you're going to get 0.99999999999. So it's going close and close to 1. So whenever you see, you don't have to actually divide it out like, I think you're learning calculus that you can divide it out like this, like n over n divided by n over n plus 1 over n. You do that, you will see it right away. So that's going to be 1 over 1, because 1 over n is going to be 0. But you can actually think about it by looking at it too. You see this, the number that's right here is irrelevant. Even if it's a million, as n gets larger, that number is going to become insignificant. So it's going to tend towards 1. So anyway, this limit is going towards e. It's heading to e because this portion right here is going to be equal to 1. When you take the limit of it, it's going to be tending to 1. And when you multiply by the e outside, you're going to get e. So remember now, based on what we know about the ratio test, what is that telling us about the original sequence that we have right here? Based on that ratio test result, what can we say? Well, 3 of you are here, so I'm waiting to hear. Well, Michaela and Lafern. Michaela, if you're talking, I can't hear you now. See, your mic is on, but I'm not hearing anything. You sure your thing is plugged in correctly? Because I see your mic coming on, but I'm not hearing you. Oh, poor Michaela. That's okay. So Anthony keeps getting disconnected. Jermaine is in and out. Michaela can't talk. So it's just me and Lafern. What is going on today? Okay. Oh, wait, hold on. I'll be right back. Come in, come in.
Hello?
Hearing you now, Michaela.
Okay, okay. Hello?
Yes, Anthony, we're hearing you.
What's happening?
Okay. Oh, hello everyone. I'm back now. All right. Sorry about that. Hey, did I hear Anthony a while ago?
I got disconnected, so I was wondering how come I didn't hear no sound when I got back.
Oh, Michaela, can you talk now?
Yes, sir.
Ah, wonderful, wonderful. Good. So everybody is here now. So back to the question. So given that L is equal to E, I don't know, I think Michaela was here going through it. What can we say about the ratio test for this sequence? Anybody?
Sir, it is unbounded.
Good. So the sequence diverges because the limit is greater than 1. Of course, you know that E is greater than 1. So that means that this sequence here diverges. Therefore, E to the N over N diverges. Why is that so? Because the L, the limit, when you do the ratio test, was greater than 1. Remember, if it is less than 1, then it converges. But if it's greater than 1, it diverges. So for those who joined late, we were testing this limit right here with the red below it. We're testing this sequence, beg pardon, by using this ratio test right here. So we checked it and you can write off that. This part down here is irrelevant. So are there any questions?
No, sir.
All right.
I had connectivity issues.
Okay. Anyone still writing? I think German has the same problem as you, Anthony, because he was on and got cut off, was on and got cut off again, and then I think he decided he can't bother to try to come back. That's my assumption. Anyone still writing? No? All right, I'm gonna give you one to try now. Try the sequence equals to 3 to the n over n factorial. Yeah, that should be interesting. Test if that converges. Any test you want. Wait, you know what? Give you some more. Number 1. Number 2. 5 pi to the n. Ah, the next one, where is it? I don't know what's just jumbled. Ah, there they are. Okay, try those two first. Then I have some more coming. Why is Sarah giving so many examples on this? So as soon as you finish testing, you can let me know what you think the result is. Is it converging? or not? Anything yet with number one?
Looks like 0. So it's it converges.
Converges to 0.
Yeah, I could be wrong.
All right. All right, so try number two. That heard Michaela. Any thoughts on number one? Or not finished yet?
Sir, I got 0.
The same as Anthony? Okay. Wait, that was Michaela. You know, I thought that your first thought was Lafern, you know. Lafern?
Yes, sir, I got 0 as well.
Wait. I hope it's right, you know. All three got 0. Okay, try number two.
Sir,
Mm-hmm.
for the The other one, would it be diverges too? That it diverges
Why do you think it's diverges?
because I use the like, is it constant test, and C would be greater than 1.
Good. Nice. But you notice you could actually have used the same ratio test. We are correct. What you did was the easier way to use the constant test. If you use ratio test, you could have done this 5 pi n plus 1 over 5 pi to the n.
And
And of
subtract.
course, oops, yeah, when you divide it, just get left with 5 pi. Of course, you'd have a limit beside it, but the limit of 5 pi is 5 pi.
Yeah.
So if it, and that is greater than 1. That's why I said the ratio test works for both the constant, works for all of them, to be honest with you. So when in doubt, use the ratio test. But what Michaela did, she used the second test, convergence test 2, which is much faster because C was greater than 0, and this thing here is C. So therefore it diverges. Anyway, let me go through number 1 quickly. 3 to the n over n factorial. Was that it? I think that was it. All right, so the limit of that. Whoops, what am I saying? That is xn. Hey, hold on, please.
3 to the n over n factorial.
Guys, give me please. Hold on, 1 minute. My phone is off. My phone is off. Let's charge it. No, not can't leave the class in the class. I said, when you come, the woman is going to look over it. Then come in, let's do this and you. Then come in. Sorry about it, everyone. I've been on and off so much today. Lots of problems today. Okay. So the 3 to the n over n factorial, I think. That's the one I gave you. So testing the limit as n tends to infinity. So we have 3 to the n plus 1 over n factorial. Whoops, n plus 1 factorial. Absolute value of that.
Sir, I'm having connection problems on my side. Keep on kicking me out.
Yeah, I realized because it kept going out and coming back.
Okay, sir.
It's been a general theme today for everyone. Well, except me and Lafferan, but Michaela have been having difficulty. Anthony was on and off as well. I'm not sure what is causing it. All right, so because everything right there is positive, we don't need the absolute value any further. You can just write 3 to the n plus 1, combine the like terms, over 3 to the n times n factorial over n plus 1 factorial. All right. So we have the limit as n tends to infinity. That's what 3 to the n into that is just 3. N factorial into the thing below it is just n plus 1. So we're left with the number 3, one little constant, over n plus 1. But remember, the n is tending to infinity. So that's going to be becoming a constant. It's going to be something like this. 3 over infinity. And remember that you learned in Cal 1 that as when you divide a constant by infinity, it's almost 0. So it's tending to 0. So because the ratio test gives us something less than 1, then xn converges and the limit is equal to 0. Yes, Anthony?
Yes, sir. Well, two things. What I said about the absolute values, you said they disappear because of what?
Because everything right there is positive. Remember, n is a natural number, so it has to be positive, and because 3 is raised to a positive number, well, 3 raised to a number, the positive number raised to a number, it has to be positive. And the n is already positive, so the factorials must be positive as well.
Okay. So we have to, so you have to state somewhere at the beginning that n is a member of natural numbers or something like that, right?
No, man, every sequence we're doing is n is natural number. All the sequences.
Oh, is
Unless otherwise stated.
okay. Oh, okay. Okay.
Yeah.
Gotcha. Gotcha. All right.
All right.
And the next thing, I think you were saying in one class that we can't put 3 over the infinity, but understood that as it approaches infinity,
Yeah,
the
that's up with the
number,
arrow.
the limit
Not equal
approaches
is
0.
approaching. Right, right. So I just did that part to show it to you, what is
Okay.
happening, but you're not supposed to write that.
Oh, okay. All right.
You're supposed to move from this one to 0.
Right.
Yeah. Those are the two questions. All right, anything else? We did
Yeah,
number 2 already? Good. So let me give you a decent one now. So those were the warm-ups. Now here's a decent sequence. Oh, sorry, go ahead.
wait, can you do the what do you call it now, the constant test? Let me see. How would you do that
Oh,
now?
for number 2?
Yeah.
All right, for number 2, can do it right down here because it's very short. I think the sequence was 5 pi to the n. I think so. 5 pi to the nth power. No. The what do you call it? The constant test gives us this. If the c is less than 1, but of course it's positive, but less than 1, then it's read it. So first of all, we know that c is greater than 0. That's the first thing in the constant test. If the c is not greater than 0, can't use the constant test. In other words, if the c is a negative number, constant test is out the door. Now, if the c is less than 1, which means it's between 0 and 1, then the limit of that sequence is going to be equal to 0. But if the c is greater than 1, then the sequence is unbounded, diverges. So in this case, our c was 5 pi, which is greater than 1. As I see here, it looks like something else. C was 5 pi, and that is greater than 1, therefore the sequence diverges. That's the constant test. Pretty simple. You got that, Anthony? So two things are testing for. If it's
Sorry,
greater than
didn't
1 or
realize.
less than 1.
I said I realized my mic was off. I said greater than 1, it is
Diverging.
divergent. Between
If it's
0
less
and
than
1.
1, converges.
Okay.
So if you just
And if it's
simply have,
less than 0.
if it's less than 0, yeah, then we can't use the constant test. The constant test only applies to positive c's.
Okay.
Mm-hmm.
Gotcha.
All right. So let me not squeeze it down there. So if the constant test is like this, first c must be greater than 0, That's the first thing. And then if the C is less than 1, converges. If it's greater than 1, diverges. So the premise is first that C must be a positive number. And you're testing the sequence C to the n. All right, so that's a constant test. And most of the tests you're going to encounter will be the constant test or ratio test. The first test is going to be mostly for the sequence you've done before. So you're going to actually be proving those rather than testing them. Because the test for that might be a bit long and tedious, and I don't want to put you through that because you might make mistakes too. I'm mostly testing these two. That's why I'm giving you some examples and then the real example I wanted to get to, well, there are two more. These two right here. Let me give you the easy one first. Test this one quickly. N over 4 to the n. Then I give you the big boss after this. Yeah, let me write it again. Write xn first. N to the 4 over n. Yeah. So I'll give you 2 or 3 minutes to test that. Does it converge or does it diverge? So as soon as you found out whether diverges or converges, let me know, No wait for me to ask.
Sorry, converges.
All right, so my friend says there's convergence. Do you have any agreements or disagreements?
sir.
Mm-hmm.
For the ratio test, right? When it's when it's equal to 0. I'm really confused.
What is equal to 0?
If the limit is equal to 0, it converges,
Okay.
right?
Well, look at, yes. I was going to make you answer it, but yes.
But otherwise, it's if it's greater than 0, it diverges.
Oh, not necessarily.
Greater than 1.
Ah, that's where diverges.
But what about when it's equal to 1?
But to be honest, I've never seen that before, but yeah, if it's a different test, in that case, it would be, what's the word? There's a word for that. It's not incomplete. It's. Why am I forgetting this word? It doesn't give you enough information. What is a word for
Okay.
it? Inconclusive. That's it.
Oh,
So you got less than 0. I mean, what you got? 0?
um, yeah, I don't know. I actually got 1.
Oh, you got 1. All right. So yours is inconclusive. Lafferand is converges. Michaela? Oh, wait. Somebody's missing. So let's see. Oh, Michaela's here. Michaela, what do you think?
Mine converges.
All right. So let's test it then. So we have 2 converging and 1 inconclusive. Let's check to see what is going on. So we have the limit as n tends to infinity. Don't worry about my n, it's a bit ugly. We have n plus 1, not factorial this time, 4n plus 1. Absolute value of that, which you shall discard soon because everything is positive. So this is the limit as n tends to infinity of put them together now. We have the 4 to the n over 4 to the n plus 1 times n plus 1 over n. Doing some further calculations, now we get n tends to infinity.
I changed my
All
answer.
right, so 1 over 4. Let's love this n plus 1 over n. I should just put n plus 1 over 4n. Anyway, it doesn't matter. The reason I'm actually going to split m is because I'm going to take out the quarter to make it even more obvious what is happening. Now, I've seen some people not sure about that because they say, sir, but then the number at the top is bigger because of the plus 1. So you see, if you have difficulty understanding what is happening with this thing here, you can do it like this. You can write it as the limit as n tends to infinity of n plus 1 over n is the same as the limit as n tends to infinity of n over n plus the limit as n tends to infinity of 1 over n. The first one is obviously 1. So it's 1 plus, and you know a limit, we already established that this limit right here is heading towards 0. There's 1 plus 0, which is just 1. So that means that this limit right here is going to be 1. So it's heading towards a quarter. Oh, so you got the 1 there, but you messed up with the 4, Anthony.
I the way which okay. I'm wondering if the way I did it is incorrect or not. Well, obviously based on the answer, but I'm seeing no part of my answer could be either. If you have the limit as n approaches infinity, and then in the bracket you have n over n times 1 over 4.
N over n times 1 over 4. Yeah.
Right. That could be separated, right? As a limit of the limit as n approaches infinity of both of them.
A quarter and n over n.
Uh-huh.
Yeah, can do that.
But But can't it be that the n over n times a quarter become n over 4n?
Mm-hmm.
N over 4n. Oh,
But it's
okay.
still a quarter.
Still a quarter, true. All right. But I was looking at it from the standpoint that if you put, let's say, put infinity inside of it,
Yeah.
is it infinity? I'm just thinking the n and the 4n. I guess 4n will be,
And so this one, like you're thinking too hard, man. You have a number, you divide the number by 4 times the same number.
mm,
It's a quarter of it.
yeah, that's true. I'm just trying to think of it in another sense. Like the 4 times infinity, would you say that it's approaching infinity faster?
4 times infinity approaching infinity.
Yeah. Well,
Yes, man, you even faster than this infinity itself.
right. And it's then the infinity itself, right?
Right. But you see, when you're thinking about these things, you're thinking about what it's heading towards. Because you see, let's say our infinity is like in the million range, because infinity is really a large number, as large as
Yeah,
you can get.
right.
So if it's like a million divided by 4 million, it's heading to a quarter. If it's 100 million divided by 400 million, still heading to a quarter. So it doesn't matter how big the number gets. If you divide it by 4 times itself, it's heading towards a quarter.
Okay. All right, gotcha.
Mm-hmm. Yeah, man. All right. So this result was a quarter, which remember that's not the answer, As you guys correctly said, it's heading towards, it converges and it's converging to 0, not a quarter. The test just tells you a value that will let you know what the sequence is converging to. So as you correctly said, n over 4 to the n is converging to 0. Well, the limit is converging to 0. Limit is going to 0. Limit is equal to 0, which means it's converging to 0. All right, so now for the real deal. So that was the warm-up, So we had some easy ones, well, decent. Then this was a little challenging. And now we're going to the real deal, or one like it. I can't give you all of them because I need to save some for your assignment or test.
Sir.
All right, so mm-hmm.
All right. So in terms of having, so you'll have a quarter, yes, as your answer, right? In terms of the limit,
Yeah,
but you will still say that it's converging to 0. Once it's approach, watch it. The limit as an approach infinity of a function is for the ratio test, you basically say it's converging to 0.
right. If it's equal to a value between 0 and 1.
Okay.
Mm-hmm. And once it is greater than 1, it doesn't matter how big it is. If it's even 1.001, diverging. Because I've seen students before when they get something that was very close to 1, but this was in calculus. And they say, sir, but it's close to 1, sir, then maybe not so. And they lose marks. So remember, less than 1, convergent, greater than 1, divergent, equal to 1, inconclusive. I wonder if I can find one that's equal to 1 and put in a test. That'd be a good one, because based on your question a while ago, you make me think of it now. But they're hard to find. I'll have to see if I can create one. All right, here's the next one now. So I'm giving you 5 minutes to try this one. So the sequence is, oh, I forgot when I write it like this. Writing like this, xn is equal to -1 to the n plus 1. What am I writing? I don't know. -1 to the n plus 1 times n plus 2 over root n. Hey man, that should give you some good times. Yes, I'm giving you 5 minutes. Take your time, please. Don't rush it. I'll be right back. Any results yet? Okay, still working on it. Yeah, but that's a tough one. Come on, guys. Nothing yet? I mean, it's tricky, but not that bad.
A few more seconds, sir.
All right.
Sir. Oh,
Mhm.
wait. Oh, wait. Sir, you don't know the answer. You know the answer, sir?
Mhm.
Is it convergence?
I don't want to say yes or no until everybody says theirs. But I'll just take
Okay.
yours as
Well,
convergence.
that's my answer. It converges.
Okay.
Yes.
Fern and Anthony.
Bounded but not convergent.
All right. That's an interesting result. Fern?
1 second, sir.
All right.
bounded over. Less than.
So it's convergent.
All right, so Lafferin says convergent, and I have some stuff to check. All right, so let's check. Oh, by the way, how you got the result, Anthony? I'm interested to hear
I
that.
don't know. What I really I got is -1 limit -1.
And your conclusion is that it's bounded but not convergent. Why is that?
Well, I'm just looking at this theorem that you gave us at some point. The sequence is -1 to the n, and it's bounded but not convergent.
Okay.
I wonder if that's. I don't know,
All right.
I don't know if
I
that
hear you.
applies, but you can clarify that concept.
Okay. All right. So Lafferin, why you said bounded? Well, let me go to Mikeda first. Show the first result. Why bounded, Mikeda? I mean, why convergent, Mikeda? What you got for your limit?
Sir, I got -1.
Oh, okay. What you got, Lafferin? Laffy? Why did
So
you say
that's what I
convergent?
got as well. I got
Well, I got
negative.
-1. So I don't need to go through it then. So you got the correct result, but then Anthony got the correct. You got the correct limit, but then they tricked you with the -1. You see that -1 to the n is going to cause it to flip flop. It's going to go over here, then over there, then positive, then negative, positive, negative. So yes, you might say, oh, -1. If you actually think about it, you're getting the inconclusive result. Forget -1. If that -1 wasn't there, it would have been 9n plus 2 over root n. So what they should have said, which I didn't tell you, so that's a flaw I'm realizing in the ratio test. In the actual wording of the ratio test, it says, well, the matter of fact, they didn't tell you at all. They said if it's less than 1, greater than 1. They didn't mention what happens at 1 and what happens at -1. -1 and +1 are the same thing in terms of if you get that result, then it is inconclusive. Now, I didn't, even though I didn't mention it, I thought you'd have picked it up because you see flip-flopping, that -1 right there is going to cause the flip-flop no matter what. Even if the sequence is converting to a particular value, because of the -1, it's going to cause it to become like -2, then +2, and it's not going to go to 0. And if you even look at it, you can see it. Let me show you. Watch carefully. I'm going to put it in black, the two important things. This one is important. And, oh no, I don't remember the question. Let's see if I can find it back. Oh, n plus 2. That one is not really important. So put it back in red. Although it isn't kind of important, no, but and everything is important. Everything is important. But you see that n at the top? That is bigger than the one below. So you're actually looking at what is happening to n and root n. If you think about it, when you divide a number by its square root, what is it heading towards? Any number divided by its square root. Forget the +2, because as the number gets bigger, it's going to go towards a specific thing. When you divide a number by its square root, what are you getting generally? It's not a trick question, you know. Hello?
The square root itself.
Yes, it's greater than the number. So even that n plus 2 at the top, the 2 is irrelevant as n gets large. Like, for example, a million plus 2 divided by the square root of a million is going to really pretty much be the square root of a million. With some decimal places, of course. So what I'm saying is you can see, just from looking at it, that it's diverging. Because as n gets larger and larger, infinity divided by the square root of infinity is just redoing infinity. If you get what I'm saying. Because square root of infinity is infinity. So without even going through that procedure we did a while ago, you can actually look at it and figure out that, wait, as n gets very large, you know, when you divide n by the square root of n, you get even really the square root of n. And what's the square root of infinity? Infinity. But anyway, the fluctuation with -1. Anyway, so make a note of this. If the L is equal to 1, it was not mentioned in the when I was looking through the textbooks. A couple of textbooks didn't mention it. I remember there was one that mentioned it when I was back in school. This one didn't. So when I gave it to you, I forgot to mention it. But if L in the ratio test is equal to 1 or -1, it's inconclusive. Generally, it's going to diverge, but we're not completely sure, so use inconclusive. I think I've seen one example where it was equal to 1, and another test showed that it converged. So that's why I don't want to say diverges. It can converge as well. But most of the time it's going to diverge. Like this one diverges.
So the answer is diverge?
Based on the ratio test, no. Because remember I asked to use the ratio test. Based on the ratio test, it's inconclusive. Yes, it diverges, but based on the ratio test, it's inconclusive.
So you'd have to use another test once
Right.
it's conclusive. All right. So what test would we use?
There's a test with -1. There's a test with this. We haven't gotten there yet, but I don't even know if this course does it. But yes, there's a test with -1 that if -1 is I need to go find it. It's possibly in this course, but I don't know for sure. If it's not, I'll just put it in there so you can know. But there's a -1 test. I don't know what they call it. Let's see if I can find it. It's an alternating test. That's the name for it. So it's because of even without this thing that I showed you right here, even without this, just because of this -1 right here to the positive to the n, is going to diverge. That alone will cause divergence, unless it was heading towards 0, which it wasn't. If it was heading towards 0 now, then it diverged. It would converge, sorry. But because it's not heading to 0 and it's heading to on another number, it cannot converge because of that -1. But when the test that I'm going to give you, I will not ask you to use that test because it's not really a part of real analysis. If it is, I missed it. I'll double check to see if it was in the textbook and I missed it because I was looking through because they're using the syllabus that was created from other colleges and stuff. So I didn't want to put something that wasn't there. But if it is there, I can put it in easy. Alternating series test is pretty easy to do.
So for our course now, once we come to -1, we just state that is inconclusive and leave it there, full marks, or we'd have to go and use another test?
No, inconclusive and leave it there, unless you're asked to do otherwise. Because what I would state, is use the ratio test, and if it's inconclusive, then use a different test. But that was if I was going to make you use something else. But if I don't state that and I said use the ratio test, you're good. Because if I said to you, use one of the 3 tests, remember I give you 3 of them? If I state use one of those 3, and of course in this case you have to use the root test, then you just stick with inconclusive and move on. Hey man, easier? Yeah. Okay. Understand nothing?
Yeah, man.
Okay, good. All right. So any other questions, guys?
Yeah. I think Jermaine is going to watch the video, but what about if he doesn't get the -1? You probably would have to do the question itself for him.
What if he doesn't? Oh, you mean work it out? Okay. You're right. -1 to the n plus 1. Was it n plus 1? Yes. N plus 2 and root n. Okay. So it's going to be the limit as n tends to infinity. So we have -1 to the n plus 2, because then we're adding 1, replacing n with n plus 1. And this will be n plus 3, and this will be root n plus 1. Replace all the n's with n plus 1. and divide. So I'm going to just go straight ahead to multiply. So it's going to flip. So up here, we're going to have root n. Down here, we're going to have negative 1 to the n plus 1. Negative. And this is n plus 2. Bracket look like that. Yeah. So we can squeeze it in right there now. Maybe I shouldn't. Next line. Limit. So I'm going to put all of them together. We're going to have the negative 1 to the n plus 2 over n plus 1. We're going to also have n plus 3 over n plus 2. And finally, what's this? Root n over n plus 1 over root n plus 1. I'm going to
Question.
go
Would you
a
have to
step
put
further. Would you have to what?
would you have to put a bracket? Would you have to put a bracket after the function itself?
After the function itself?
Sequence. After the limit of n approaches infinity, you put an open bracket and close it just before the equal
It's best to
sign.
do that.
So you know it's the limit of everything.
Yeah, generally it's best to do that.
Oh, okay.
I'm just being lazy because I know you guys know what is happening. But it's best to do that, yes. Because if you don't do that, you might be saying, okay, limit of the first part, then times the rest. So it makes sense to put it. Make sure it makes up everything.
Okay.
All right, for the first one, now let's break them down. So this is going to be limit n tends to infinity. That was negative 1.
That'll be negative 1.
This over here can't go any further. Matter of fact, let me put a separate limit for it. Well, matter of fact, the rest of them can't go any further. So I'll just put them back then. N plus 3, n plus 2.
Wouldn't those be n over n, which is 1? Like,
You can't split them. You can't put n over n then plus 3 over 2. You can't split that. What do you mean? Is that what you mean?
yeah, as n approaches infinity, like the plus 3 and the plus 2 doesn't make sense. So you just put
Oh,
n over n.
right. Well, I want to say you can't
So you could
just
have
write
just put
equal.
1.
You're going to put 1 now. But I mean, you could have put the 1 in the limit after you remove the limit. So it's negative 1 now times 1 times 1, which is negative 1.
Gotcha.
Yeah. So the limit, as Anthony's mentioned a while ago, as n gets very large, like probably when n is 0, that's 1.5. When n is 1, that's what 4 over 3. 1.3333334 whatever. But as n gets larger and larger, it's going close and close to 1. And by the time n gets like over 10 trillion or whatever, that 3 and that 2 is quite irrelevant. It's almost like you're dividing and getting 1. You get 0.9999999, probably a million nines, which is pretty much 1. So anyway, and the same thing for the square root. That one is almost irrelevant. Even by the time I get to 1,000, that one is almost irrelevant. So oh, Anthony's gone. Anyway, so that's how the negative one was arrived at. I'm hoping that's what Michaela and Lafern did. Please confirm, Michaela and Lafern. You did something like that?
Yes, sir. Same thing.
Okay, good. Lafern, your copy? Or you did the same thing?
Did something similar, but got the same result.
Okay.
I got this.
All right, so next class, I realized I'm surprised that you're back because I
You
was
heard
really sure that you were still connecting. Yeah, I'm here. Go ahead.
Was asking now, could you, in place of n plus 3 over n plus 2 in the second to last step, could you have put n over n? Or that I do that either?
No, you can do that.
Okay.
It's pretty much the same as that, but it's actually not equal to it. If you're saying that something is equal to it, what you could have said is that it's less than or greater than or something like that, but you can't say it's equal. If you put equal, you lose mark.
Not to put equal, but when you have the second to the last step, we have the limit.
I know, but what you'll be saying is that the third to last is equal to your one n over n. But it's not equal to it.
That's true. Okay, so you
basically you lose marks for the equality. If you had put an arrow, like saying that it's implying that, then you'll be okay. If you put equal, you're going to lose marks.
Okay.
If you get what I'm saying.
Right. Okay. I'm just trying to
In the same way we're
figure out how to set it up where you have like n over n, so you actually know it comes down to 1, or you just basically just put. Okay, I think I know what. Where I have the equal sign in the last step, I could have put -1 and then put n over n, and then times root n over root n, and then put equal without the limit part of it.
oh. I suppose I could do that. Yeah, you could do that. You could do that. Yes. You mean removing the limit now?
Yeah, when you remove the limit,
N over n.
I could put n
Yeah,
over
yeah,
n.
yeah, could do that. Could do that.
Okay, all right. Thanks.
That's fine. Because remember, you know, the method they used to actually prove that that is equal to 1, you know, was actually this thing. You have the limit, and then you have the n over n, 3 over n, n over n, and 2 over n. That's how they actually proved it. We are just going without doing that because we know it already. So this will give us the 1 plus the 3 over n, and then the 1 plus the 2 over n. Now, because we know that the limit as n tends to infinity for that result is going to be 1 plus 0. That's how they actually get around doing to show that's equal to 1.
Yeah.
So we know that already, that's how we just go straight to 1. But if you actually wanted to prove it, that's what you'd have to do.
Okay, gotcha.
All right, guys, so stopping here. Next class, I'm going to be starting, probably looking at a little bit at Cauchy sequences. And then we're going to go to, what's that topic again? The final topic, what was it? Continuous functions, right?
Okay.
Which was actually optional, but if anything, I might skip that and go to derivative, you know, because derivative is nice.
Which one?
I'll
Skip
think
what?
about it. It's either going to be continuous or derivative. Repeat that?
You're not gonna skip Cauchy, though?
No, man, we're doing Cauchy next class.
Okay, good.
Cauchy is set, and it's either continuous or derivative, one of those two.
Okay.
Cauchy sequences are important.
Derivative, just derivative? What you call it?
The derivative includes the mean value theorem, the Taylor's theorem, and the inverse function theorem.
Yeah, man.
The
That's
whole thing is derivative.
okay. That sounds good. I think that's important. That helped me with complex analysis, sir.
Right. Oh, it's in that too.
Yeah.
Okay.
But from a complex analysis standpoint, the
Perspective.
imaginary
Yeah, I get you.
numbers.
Oh,